Okay, here's how to show an existential statement is false. So here's an example. Prove this is false, is what it will say. There exists an integer m greater than or equal to 3 such that this is prime. Okay, so what we're going to do is we're going to take its negation. So here's the negation. For all m in the integers, m squared minus 1 is composite, not prime, right? The opposite of prime is composite. So I've changed it from a there exists to a for all. Okay, so here's the proof. So you have to state this. I mean, all of this is the solution, right? So first you have to state the negation and then start proving. So take this and factor it. So I've got two factors. And so to be composite, remember, all goes back to the definition. So the definition gave it in terms of R and S, right? Where each of these factors were between 1 and n. So I'm going to use R and S. So here's R and here's S. And then since I have this criteria here, m is greater than or equal to 3, then I get both R and S are bigger than 1. And so that must mean that m squared minus 1 is equal to r times s, where the r is between 1 and the number, and the s is between 1 and the number is m squared minus 1. So that must mean it's composite. So proving things forward, you're proving using the definitions. All right, so I'll have I'll do some, and then I'm going to leave some for you to do. Okay, so prove this is false. So first off, I'm going to state the negation. So I'm even going to write it. So it's nice to communicate to your reader, i.e. me, what you're doing, right? So this is a for all. So I'm going to make a there exists A and B in the real numbers, right? And if I made it a there exists, I have to put the word such that. And remember here, I'm taking the negation of an if then. Such that, and then I'll have A less than B and not this, right? So I'm going to rewrite it with not that. So I'm going to make it A squared is greater than or equal to B squared. Okay, so I'm trying to prove this negation is true, right? I want to show this is true, and then that means this will be false. So there exists means, oh yeah, I just have to find one that makes it true, right? I want to find examples that make this true. So can you think of an A that's smaller than a B, where the A squared is bigger than or equal to the B squared? How about A equal -1 and B equal 1/2? So here A is less than B, right? And then if I want to take A squared, is it bigger than or equal to B squared? So if I take A squared, I get 1. And is that bigger than or equal to 1/4? It is. So this is an example of showed that this exists. The negation is true. That means the original is false. All right. So here's more of the more common kind of problems. Prove this, prove this. So these aren't as common, just so you know. Okay, so first I'm going to rewrite it formally so I get some letters in here, right? So for any n in the even integers, and this is one way to write n even, comma, n squared is even, right? Okay, so I'm going to start off with the definition. Since n is even, n can be written as 2k, comma, then you need to say k is an element of the integers. So then I'm going to say, okay, so n squared will be 2k squared. So you have to start off with this, make the substitution. This is 4k squared, and then I just have to rewrite it so I can say it's 2 times something. So if I factor out a 2, just bring it over here, I get 2p, where p is equal to 2k squared, comma, p is an element of the integers. So here I've written n squared as 2 times p, so therefore n squared is even. Check. All right. Prove that the difference of any even integer minus any odd integer is odd. All right, so let's restate it first. So any, so for every I'll put n is an element of the evens, comma, m is an element of the odd integers, right? Those are z's. Sorry, they're kind of messy. So for every comma, n minus m is odd. All right, so starting with the definitions, n is even. That means n is equal to 2k, comma, k is an element of the integers. M is odd. M is equal to 2k plus 1. Oops, I can't use k. Can't use k. Have to use a different letter. So I'll put in t, where t is an element of the integers. Okay, so now let's put it together. So n minus m, making the substitutions, 2k minus 2t plus 1. So that gives me 2k minus 2t minus 1. Oh dear. I want to be able to say this can be written as 2k plus 1 if I'm going to have it odd. How am I going to get a plus 1 in here? All right, here is a clever trick I'm going to want you to remember, and I'm showing it to you now. So let's bring this back up here. So n minus m is equal to 2k minus 2t minus 1. All right, so now I'm going to add 1 and subtract 1. So if I add 1 and subtract 1, and actually I'm going to subtract 1 and then add 1, doesn't matter, right, what order I do it in. I haven't changed anything. So now what I'm going to do is I'm going to join these two together. That makes a -2, and then I have a plus 1. Now I can factor the 2 out of the first 3 terms. And so then I can say, let p equal k minus t minus 1. P is an element of the integers. So n minus m will be 2p plus 1, therefore odd. Okay, so make sure remember that little trick there. So let me finish this last one. Prove that the sum of any two odd integers is even. Okay, so for any n element of odd, m plus n is even. Okay, so start with the definition. M is odd, so 2k plus 1. K is an element of the integers. N is equal to 2t plus 1. T is an element of the integers. So m plus n will equal 2k plus 1 plus 2t plus 1. So I get 2k plus 2t. Oh, and these two make a 2. So I can factor a 2 out. And I can say m plus n is equal to 2p, where p is equal to k plus t plus 1, comma, p is an element of the integers. So therefore, even.